Which is going to be about workflows in AiiDA. And in some ways, the workflows is the most advanced part of the code in terms of it requires you to sort of learn a few things to really exploit them to their maximum. But once you do, the gains can be quite large in terms of automating the sequence of steps that you might want to do for a high throughput calculation. It simply wouldn't be possible otherwise. So before I go into the actual slides, the sort of philosophy that we tried to go for in writing the workflows, and what I'm about to show you is a brand new rewrite of the whole workflow engine. So we did have one that works successfully and can do a lot, and Nicolas Monet has used it extensively for hundreds of thousands of structures. But merci. But we found that it was quite cumbersome to do certain things, in particular things like debugging, right, which is something that you're going to be doing all the time because as you're writing it, it's not going to work, you're going to add bits, you're going to need to see what's going on at each stage. So our focus for this one has been, A, to stick as close as possible to just standard Python, so you don't need to learn too much more than what you already know, and B, to make it as easy as possible to debug things when they do go wrong and continue a workflow that is stopped halfway through, and so on and so on. So I'll show you what it's all about. Okay, so here's a function that basically just takes a crystal structure and a scale factor and scales the structure by that amount. And we're using the ASC library to do the scaling for us because we don't have manipulation tools in AiiDA directly to do it. So all we do is get a structure from an ASC structure from an AiiDA structure, copy it, rescale it, and then return the new structure. Okay, that's just normal Python using some of the AiiDA stuff, but it's fairly straightforward. And to use that, I would, for example, load a node and then call the function. Fine. But that has a problem, right? If you were to do this, and you're perfectly at liberty to do it, you would actually lose all the provenance of what happens here. So when you return a new structure from this function, that structure would appear in the database if you stored it, but it would have no incoming links because you don't know where it's come from. But clearly, looking at your code, you know that you've taken a structure that was in the database, you've put it in the code, and out has come a new structure. Clearly, that's the function that's acted on the original structure, and you want that association to be stored in the database. So to do that, in this case, all you need to do is get this import and decorate it with this @wf, which stands for work function. And then automatically, without changing any of the rest of the code, AiiDA will preserve all the provenance in between, by which I mean there'll be an input link of a structure, a box to represent the calculation of rescaling it, and then an output link to the new structure that you've returned in the return statement from the work function. Everything else works for you. It's all stored for you in the database as you go through, and it's all fine. There are obviously certain restrictions. The work functions as parameters need to take in AiiDA data types. You can't just pass them an integer or an array, because integers and arrays in Python don't know anything about their provenance. They don't carry around the information about where they are in the database. So these need to be AiiDA types, but you're already working with those most of the time anyway. So this is an AiiDA structure. And this is an AiiDA float. It's a particular data type that we have that knows its provenance in the database. Okay, so that works perfectly well. You can effectively write a workflow. Say I want to do an equation of state calculation. I can write a workflow just by writing a function. So the function that I write, equation of state, has some steps. It takes my structure and some scale. It loops, does a loop, and then it calls other functions like this rescale that I had up before, and maybe another function called runDFT, which inside it might decide what settings to use and whatnot. Because it's got this decorator, WF, everything that happens not only coming into it, but also inside it is stored. And if you were to look in the database, and there's some diagrams in your handouts, you would actually see there's the equation of state function, which then has a call link, by which we mean it called another work function with some input parameters. Those input parameters are linked and got some results. That's then the structure goes back in there, does some things, and you would all see this in the graph, and the provenance is preserved, and you can always query and see what happened in the past. So that's a workflow, right? And all you had to do is write a Python function and then decorate it, and that's about it. So hopefully that sort of meets one of our goals of making writing these kind of workflows as close to Python as possible. But it does have some problems. So if you imagine here, when I call run DFT, right, that is going to fire off some remote calculations on a remote cluster, and there's a number of things that could happen in between. This is quite a long-running call. You know, that could take hours, it could take days. So what happens if my computer crashes in between, or I want to turn my computer off, or there's a problem with the supercomputer and, you know, halfway through this loop it crashes? Well, clearly I've lost, not everything that's done up to that point is preserved, but there's no way for me to continue this workflow and fire it back up and say, okay, now my computer's back alive, I want to restart from where I was. Because what that would take is for me to sort of go to this line in the code, make sure all the variables are set to what they were before, which just simply is, well, borderline impossible in Python. So it has a restriction. So to deal with that, we have implemented another slightly more heavyweight way of writing workflows that does allow you to solve these problems. And what we were thinking is, what we want is to lay out the steps in a sort of logical way of what our workflow is going to do. And of course, you can change those steps as you go. And the way that you would do that in code, so the equivalent of this sort of pseudocode, is to actually create a class called a fragmented work function. Fragmented because we've taken the work functions up, we split them into fragments, which are represented by these steps. And once we've got our class, we just need to define this function and tell the specifications object, what the outline of our workflow is going to be. Now, the way that you actually split up your workflow is such that anytime you need to do some kind of long-running calculation or wait for something to happen, it will be done at the boundary of one of these steps. Because at each one of these steps, AiiDA will checkpoint everything that's happened, store all the variables, continue to run in the background your calculation on the remote computer, whatever it is. And then you can always restart it. If things crash or you want to shut down your computer, you can shut down your Python instance, no problem. And then when you restart it, it'll carry on from there and continue. Or if something on the supercomputer crashes, that means that your value wasn't calculated correctly, you can go back and continue from where you were, and it'll just pick up from where it left off. And then to run it, it's pretty much the same. You have to, for example, if you want to ask the daemon to run it, so it's running in the background, you need to import this guy, async-d, so an asynchronous execution using the daemon. And then the rest is pretty similar. You load your node and call async-d. And then in this case, I give the name of my class and the inputs just after that. And it'll know what to do, and it'll submit it to the daemon. You have to make sure your daemon's running for this to do anything. But other than that, it'll take care of the rest for you. So what about my code, right? I showed you, like, this is the outline, but clearly I need to actually put the code in to tell it what to do. The outline can only contain simple commands. They're all, you can see they're all CLS, so class, and I'm telling it what functions to call. Now I need to actually define those functions. So inside my class, further down, I would create the functions, and the inputs for these functions is always obviously self, because you need it because it's a member method, and CTX, which stands for the context. Now, context is the place that we store variables that we want to persist between steps. So clearly, like all functions, if I just say, you know, a equals 5, at the end of that function, that a is gone because it has what's called a local scope, and that scope, it terminates at the end of the function. But I can use the context to store anything that I want to keep track of in between steps. So clearly, things like the scale, you know, what point am I through the equation of states? I need to store such that I can access it in different parts of my workflow or the fragmented work function. So, and I can just create them happily by saying ctx dot, give it a name, put a value in it. And what happens here is I'm actually calling a special function called result to context. And that's something where if you want to run something that's going to take a while, like a DFT calculation, you can say, okay, take that DFT calculation, submit it, so I do self.submit with some inputs, and then once you're done, save the result to my context, but don't continue with the next step until that's done. So it's effectively a sort of wait for it. You know, it says, go away, do this. When you're done, go to the next step of my workflow. And that's precisely the mechanism that allows us to shut down the daemon in between, because you can just shut down your computer, things on the remote cluster will continue to work. As soon as you restart your daemon, it will check what stage it got to, check if your thing's ready yet. If it is, it'll start the next step in the workflow, giving you your context back. And of course, now the value of R in my context will be set to the result of running that DFT calculation. So let's say my DFT calculation gives me out an energy. Well, I can go to the results, the output parameters, go to the dictionary, get the energy out, save it, and then use the context to up the scale to the next point in the equation of states I want to go to, and then loop around. And actually, you can see the way that the loop's happening is from my original definition in my fragmented work function, I've got these special constructs like while, or you'll see an if as well, that allows you to do simple branching and looping inside your workflow, because without it, it's impossible. You always need some kind of logic that it can decide on. And then once I'm done, I can just plot the results and my work function finishes. So to put them side by side, so here's, I mean, this isn't by any means the only way to code this, but here's the two equation of state workflows, if you like, done as a work function and as the corresponding fragmented work function. It's not too many more lines, but there is certainly more to write. And what I would say is, you know, in the first instance, it's perfectly fine to just start writing work functions. One thing we try to do is make it as easy as possible to go from one to the other, so that you can write it as a work function and then change it for this class-based fragmented work function that you can really run in high throughput mode, because it's unrealistic to expect that you'll keep running your computer all the time. You'll need to shut it down, or things might happen. You might need to continue. So yes, you need to write more code, but in a way, if you need this additional functionality of, you know, checkpoints between fragments that allow you to continue on crashes, shut down the computer between steps, trace the progress as it's going along, and also if you want this ability to sort of debug and see what's going, for example, there's commands you'll see in the tutorial to get things like the current status, what's stored in the context, things like this. You'll need to use the class-based, more complicated fragmented work functions. There's no way around it. If you don't need all of that and you just want to do quick calculations or test things out, just do the simple work functions and it'll be fine, and all the provenance will be preserved, so you can always query for what happened in your workflows.